Hello everyone and welcome to the next session of the P block elements. So in the P block elements we were dealing with the boron family, right? So in boron family we have the following elements such as followed by aluminium, gallium, indium, thallium, right? And the last one was anunturium, UUT. Okay, so for today, what we are going to do is we are going to take a look into the different properties associated with these particular elements. Okay, so as we start, we'll start our first property, and that particular property is going to be associated with the oxidation states. The oxidation states and reactivities. So, when we observe these particular elements, these elements have a tendency to exhibit two important oxidation states, and that is, first one, that is an oxidation state as +1, and the next oxidation state is +3. Okay, so here in this particular case, what is going to happen is as we travel down this particular group, okay, the stability of the compounds with oxidation state as +1. Okay, +1, it increases. Okay, that means more number of elements tend to show the compounds having an oxidation state of +1. Okay, so as we go down the particular group, the oxidation state of +1 increases. This is one of the important statements that you have to remember. While speaking about boron, if we stick ourselves to boron, so what this particular boron is going to do is, it tends to consistently exhibit an oxidation state of +3 in the compounds. As we speak about the stability, that means the stability of the compounds, this particular boron exhibits +3, most of them, again +3. As we travel down, the tendency to exhibit +3 goes on decreasing. Okay, that means for these particular elements, aluminium has a least tendency to exhibit +1 oxidation state. The next one, that is after aluminium, gallium, after gallium, indium, thallium. Okay, these particular elements, whatever the compounds they are going to form, they are going to exhibit more of a +3 oxidation state. Okay, so remember, it is going to exhibit +3 oxidation state, more of these particular compounds. Okay, now the question that arises is why these particular compounds are exhibiting more of a +1 oxidation state. Okay, it is all attributed to the particular elements of the d and f orbital electrons. Now these particular electrons, which the heavier elements have, okay, these give rise to poor shielding effect. Now, due to the poor shielding effect, the electrons which are present in the outermost orbit, they are not coming into the reaction. They are not participating in reactions, especially the electrons of ns orbital. Okay, so ns electrons are not participating in the reactions. due to which what is going to happen is they are going to exhibit an inert pair effect. So remember, the inert pair effect is generated because of the poor shielding effects of d and f orbital electrons of the heavier elements, due to which these ns electrons are not participating in any reaction, therefore they are inert. Okay, so it's called as an inert pair effect. Okay, so these particular electrons are not coming for the bonding, they are not utilized for bonding, thus it's an inert pair effect. Now when we observe the elements such as, let's say, TLOH, okay, now here thallium, okay, it is going to exhibit more of a +1 oxidation state. Okay, because the tendency to form +1 oxidation state goes on increasing. That's what we already have discussed. The stability of compounds with an oxidation state of +1 increases down the group. Now here, what is going to happen is when thallium hydroxide, which is exhibiting a +1 oxidation state, it shows the properties very similar to those of NaOH, KOH, etc. Now, when it is showing us the properties equivalent to that of the sodium hydroxide, potassium hydroxide, in short, I mean to say that it is exhibiting an ionic character, or I can say as an ionic nature. Okay. On the other hand, there are compounds such as TL twice CO3. So in these particular compounds, these compounds are showing us the characters very similar to that of Na2CO3, K2CO3, etc. Okay, again, there is a resemblance of the properties. Now, whether thallium is exhibiting +1 effect or whether it is exhibiting +3 oxidation effect. Okay, remember always, +1 oxidation state is always more prominent than +3 oxidation state. So this is one of the most important criteria what we have to remember under the oxidation states. So under the oxidation states, first thing that what we have to remember is all of these particular elements have a tendency to exhibit two types of oxidation states. One, +1, second one, +3. The tendency to exhibit +1 oxidation state goes on increasing as we travel down the particular group in a boron family. Now here, the stability of a compound with +1 oxidation state goes on increasing down a particular given group. Okay, so second thing that what we have to remember is, of course, boron can show +3 oxidation state only in its compounds. Next one, what is a major reason why these particular compounds are exhibiting +1 effect? It's all because of the involvement of d and f orbital electrons. These provide poor shielding effect. Due to the poor shielding effect, the outermost ns electrons are not available for bonding, due to which it exhibits an effect, what we call it as an inert pair effect. Okay, next one, what we see is as we go down the particular group towards the heavier element, the heavier element of course can show +1 and +3 oxidation state, but +1 state is more predominant because stability increases. Now, here, whenever we observe the compounds of thallium hydroxide or thallium carbonate, it resembles with the hydroxides and carbonates of the s block elements, thus giving us a hint of ionic characters. Speaking about the next property, and that is the reactivities. With air. Okay, so in air, these particular elements tend to react with oxygen and with nitrogen. So when we observe the first one, and that is boron. So boron naturally exists in two physical states, and the one physical state, that is the crystalline state. This crystalline state is actually inert. Inert in a sense, it is not going to react with oxygen. Quite simple as that. So the inert form of boron is crystalline in nature. Okay. Therefore, it is not going to show any particular reaction. Well, when we observe about the second state, and that is the amorphous state. Okay, so when we observe this amorphous state, what we observe is boron readily reacts when taken in its amorphous condition in order to form the oxides. And that particular oxide is B2O3, boron oxides. Okay, so now, here, whenever we look at a reaction, boron plus oxygen in order to give B2O3, so 2, 3, so if I take it over here as 2, so 4, right? So therefore, 4 borons giving rise to 2 into 2, 4 borons. So this is the reaction, what we can expect. Okay, so speaking about the next element, and that is aluminium. When we observe about aluminium here, what we see about aluminium is that if we take an aluminium cube, this aluminium readily reacts with an oxygen. Okay, so if we speak about an aluminium cube, let's say this is a cube of aluminium. Okay, now here what happens is this aluminium readily reacts in order to form the oxides, but the oxides are present only on its surfaces, only on these surfaces. That means the internal matter is not oxidized. Okay, so therefore what we can say is here is that aluminium on the surface reacts in order to form Al2O3, aluminium oxide. Okay, which forms a protective, film on the surface. Okay, so this one protective film we are getting on the surface, which is preventing the inside material in order to get oxidized. Okay, so therefore it prevents the internal aluminium elements from oxidation. Right? So this is very, very important for us to remember. Aluminium does readily react in order to give aluminium oxide, but this particular oxide film is present only on the surface. Internal matter is not going to get oxidized. Right? So this is what we have to remember. Now, speaking about the oxides and hydroxides from their acidic and basic natures. Now, when we observe about boron, whether it is boron oxide or whether it is the trioxides. Now, this particular compound, what is going to happen is it is going to show us acidic nature. First point. That means it has a tendency to react with base. Especially it reacts with metals. It reacts with metals in order to give us metal borates. So this is again an important point for us. Metal borates are formed because boron oxides and trioxides are acidic in nature and they tend to react with the bases and with metals. Okay, when we observe about aluminium, so aluminium oxides are amphoteric in nature. Now, amphoteric in nature, in a sense, these oxides have a tendency to react with acids as well as with the bases. Okay. So, is it true when we observe about gallium oxides? So, even the gallium oxides are amphoteric, that means they are going to react with the acids as well as with the bases. Okay. Now, when we observe about the thallium and indium oxides, these particular oxides are basic in nature. Okay, so to sum up entirely what we have. First one, the boron oxides and trioxides tend to give us acidic nature, which reacts with base and also with metals in order to form borates. Aluminium and gallium oxides, these are amphoteric in their nature. That means it is going to react with both the acids as well as with the bases. Correct? While when we observe about the indium oxides and thallium oxides, these are basic in nature. That means it is going to react with acids. Now, this was one part of this. In short, if you observe any of these particular elements, if we represent it by M, when they react with oxygen, they form M2O3. In order to balance it, 2 into 3 is 6 oxygens, so 6 oxygens here, 2 into 2 is 4, 4. Now this represents a general reaction wherein you can replace M as the metals from aluminium, gallium, indium, thallium. Right? Now, air. You have seen what will happen if we are going to take metals and react this one with the oxygen, which is present in air. Now, you are going to observe what will happen if we have, instead of oxygen, how it reacts with the nitrogen. So, when we observe about these particular reactions, usually the metals react with nitrogen in order to give compound of the type Mn, provided the metal is aluminium, gallium, thallium, indium. Now here, these compounds we call them as nitrites. Okay, in order to balance it, let's take here as 2, here as 2. Okay, so you have boron nitride. Okay, similarly you have aluminum nitride, gallium nitride, indium nitride, thallium nitride. Okay, now here one thing that we have to observe is whenever it is forming nitrides. Okay, now first when we observe about barium nitride, it is much more acidic in its nature. As we travel down this particular curve, okay, the acidic character goes on decreasing. In short, basic character goes on building up. So therefore, as we travel from the top to the bottom, what we observe is the acidic characters. Okay, the acidic character goes on decreasing in case of the boron family nitrides. Okay, we'll observe the next property. Proceeding with the next one, and that is going to be the reactivity with acids and bases. Okay, so when we observe about the reactivity of the boron family elements with acids and bases, the first thing that what we note is here, boron. This particular element neither reacts with acids, neither it reacts with bases. That means boron is inert. It does not react with acids or with bases. Okay, on the other hand, when we observe about aluminium, so aluminium, as we have already spoken about its amphoteric nature, it tends to react with, it reacts with acids and bases in order to liberate dihydrogen gas. Let's observe one particular reaction. For example, if we have aluminium reacting with acids such as HCl. So here, what will happen is AlCl3, aluminum chloride, plus this hydrogen is going to be liberated. Okay, in order to balance it, let's take over here as 2Al. So here it becomes as 2 aluminum. 2 into 3 is 6, and therefore we need to have here as 6. So 6 hydrogens, but here there are 2 hydrogens. In order to balance it, let's take over here as 3. Okay, so now what happens if we are going to react this aluminium with, instead of HCl, let's take concentrated nitric acid HNO3. So it gets oxidized Al2O3, okay, forming an passive oxide layer, after which gives water, along with water okay, so in order to balance it, we have taken as 2, so 2 over here. Now 6 HNO3, therefore there should be 6 NO2 that is liberated. Okay, so in short, it is going to react with both acids and bases. Okay, so we can also have reaction of aluminium with sodium hydroxide. So when it reacts with sodium hydroxide, it gives a particular complex, 2Na plus over here, AlOH 4 times plus 3H2 that is liberated. Okay, so in order to balance this, let's take over here as 2, 2, alright. So this particular section we call it as sodium tetra because we have 4 hydroxide. Okay, OH. So what remains is 8. We have 1, 2, and 3. Okay, so this is the name of the complex, which is formed. As we might observe the next particular reaction, and that is the reactivity with halogens. Okay, so in this particular section, what we observe is these particular metals tend to react. Let's observe it as M for these particular metals. They tend to react with halogens in order to give the compounds of the type MX3. Okay, so In order to balance it, let's take over here as 2. So 2 into 3 is 6. So therefore, let's take over here as 3. Right? So it is perfectly balanced. Now these particular type of halides are formed, but with an exception. Exception is of thallium iodide. This particular compound is not formed. Okay. Now, when we observe about boron, let's say that we have boron halide, so BX3. What are the important features that one would expect? So, from a boron halide, what we see is the first important thing that we have noticed, these particular compounds are covalent in their character. Secondly, in this particular case, boron is sp2 hybridized. Okay. When we observe the shape, it is trigonal planar in its structure. So these are 3 important points that we have to remember about the boron halides. If we observe about the different halides such as BF3, BCl3, BR3, BI3, right? Boron fluoride, boron chloride, boron bromide, boron iodide. Now here, all of these particular elements are monomeric in their nature. That means all of these are formed of the simple single structures. Secondly, all of these are volatile in nature. These particular compounds are highly reactive in this particular form. Okay, so these are the important things what we have to remember. When we speak about their states, physical state, these two are formed in the gaseous state, while bromide is formed in liquid state. Finally, boron iodide. This one is formed in solid state. Okay, all of these do not conduct electricity. Remember, they do not conduct electricity at the boiling point. The boiling point of these compounds are found to be low than the compounds, or you can say as the halides of the first and second group elements. That means about the S block we are speaking here. Okay, so therefore, remember, the boiling points of these particular compounds are found to be lower than the particular compounds or the halides which are formed from the elements of first and second group respectively. Now, one more important aspect that what we have to deal here is with the fluorides of all of these particular compounds. That is, let's say, aluminum fluoride, gallium fluoride, indium fluoride, thallium fluoride. These particular compounds. Now, these are actually ionic in nature. While when we observe here, these particular compounds are covalent in nature. So therefore, I have not included BF3 in this case. So aluminum fluoride onwards, all of these are ionic in nature. Of course, the rest or the other halide of elements are covalent in nature. Okay, so this is important point what we have to remember. Secondly, the boiling point. The boiling points are quite high. Third point what we have to understand is these particular metals on hydrolysis, it yields compounds such as MOH 4 times, negative charge all over the complex, H2O 6 times, minus 3 times. So these are the compounds which are formed once we try to hydrolyze these halides. Okay, we'll discuss about the next properties in the next video.